Spatial memory. The world's representation is the robot's spatial memory. Spatial memory supports 4 basic functions. Attention, what features or landmarks to look for? Reasoning, can the robot fit through a space? Path planning, what is the best way through this space? Information collection, what does this place look like? Have I been here before? Has anything changed? Forms of spatial memory. There are 4 forms of spatial memory that we will discuss here. They are route, layout, relational, and associative. In route or qualitative, you express space in terms of the connections between landmarks. It's an egocentric view. For example, go to the stop sign and make a left at McDonald's. Layout or metric is quantitative. It expresses space in a metric representation that has some approximate scale to estimate distances to travel. That's a bird's eye view. Layout representations can be used to generate a route representation, but not necessarily vice versa. Relational, which is the most popular because the robot connects the dots. You focus on graph-like representation of spatial memory. Relational techniques support path planning. Associative. Associative focuses on coupling of sensing with localization. It parallels the tight coupling of sensing to action found in reflexive behaviors. Associative techniques support retracing known paths. Topological navigation. Topological navigation depends on the presence of landmarks. A landmark is a perceptually distinctive feature of interest on an object or locale of interest, for example, a red door or the McDonald's arch. A gateway is an opportunity for a robot to change its overall direction of navigation, for example, at the intersection of 2 hallways. Landmarks can be artificial, which means they're added to an object or locale to support recognition, for example, interstate highway exits, or they can be natural, configurations of existing figures for recognition, for example, McDonald's golden arches. They should be readily recognizable, support the task-dependent activity, and finally, a landmark should be perceivable from many different viewpoints. Topological path planning. A relational graph has nodes which represent landmarks, gateways, and goal locations. The gateways are opportunities for the robot to change the path heading, and the edges of the relational graph represent a navigable path. Here's another example of a relational graph. The following floor plan has been made into a relational graph. Each edge should be labeled with the appropriate local control strategy, such as MTD, move through the door, or FH, follow hallway. Each node should be labeled with the type of gateway. For example, a T would stand for T-junction. A D with E would stand for dead end, or R would stand for room, such as room 1, 2, 3, or 4. Transition table. The transition table shows how to move from one node to the next by using a local control strategy if one exists. For example, it is not possible to go directly from room to room. Therefore, there's no local control strategy. However, it is possible to move from a dead end to a T-junction by using the follow hallway control strategy. Qualitative navigation means to localize a vehicle to a particular orientation region. An orientation region, or OR, is a patch of the world defined by landmark pair boundaries. A landmark pair boundary is an imaginary line drawn between 2 landmarks. The robot creates an outdoor topological map as it explores the world. It can coarsely localize itself to a metric map by using these boundaries. Path planning and execution are deliberative. A cartographer maintains a map in the form of a graph and monitors progress. A transition table would be the high-level sequencer, which we just discussed, and scripts specify and carry out the implied details of the plan. Distinctive places. A distinctive place is a landmark that the robot could detect from a nearby region called a neighborhood. Based upon cognitive science, the lowest level of representing space are landmarks such as doors or hallways, and procedural knowledge to travel between them. Local control strategies are like follow hall or move through door. The next level of representing space is topological, which supports planning and reasoning in a relational graph. The uppermost level is metric, where the agent learning distance and orientation between landmarks in a fixed coordinated system. Higher layers represent increasing intelligence. The robot uses one behavior until it sees a distinctive place, and then it uses a different behavior when it's in the neighborhood near the landmark to localize itself. Behaviors serve as local control strategies and releasers that signal the interest to a neighborhood. Visual homing. Visual homing is the use of image signature to direct a robot to a specific location. An image signature is created by partitioning an image of a landmark or location into sections. If the robot is in the neighborhood of the location, then the image measurement should be approximately the same pattern. Here we see a very coarse example of this, where the image signature has been discretized enough so the robot recognizes that it's near the house and the tree. What are some of the advantages and disadvantages of topological navigation? It does eliminate navigational errors at each node and build up a reasonable metric map. It does support discovery of new landmarks as the robot explores an unknown environment. However, a disadvantage is that a landmark must be unique at a node pair, and sometimes good distinctive places are hard to perceive. Gateways are hard to perceive. Landmarks were not locally unique, then you'll have a problem with the robot localizing itself, and there are also indistinguishable locations in the world. This concludes today's lecture on topological navigation. Have a robotastic day!